So today, this is the number 19th open seminar in Frontier of Nuclear Physics, and this seminar is held by Fudan University Institute of Modern Physics, the key lab of nuclear physics and ion beam application. And this seminar is also supported by the Academic Journal of Nuclear Science and Techniques and live streamed by the cochair.com website. So today, it's our great pleasure to have the speaker, Professor Laura Fabbietti from Technical University of Munich. For those of you who works in Alice and around Sun, you must already know her. But for those of you who are not very familiar with her, let me briefly introduce a little bit. So Laura is a professor at physics department TUM. She's a group leader of the dense and strange hadronic matter study. She got a master in University of Milan in 1998 and the PhD in Munich in 2003. Later on, she works as a postdoc in various institutes such as GSI. And since 2011, she's taken the current position in TUM. Laura is an experimentalist. She basically basically works on the collaborations such as HADES, 4Pi and at GSI and LHC Alice at CERN. She used to serve as a convener of the strangeness working group at HADES and now is serving as a convener of the correlation fluctuation physics working group in Alice. So she's also the referee for the Humboldt Foundation and a member of the National Scientific Committee of the INFAN. She's awarded as one of the first appointed female professor in physics by the Bavaria Academy of Science and also many other honors, such as the most valued reviewer of the journal Physics Letter B. In recent years, based on the Alice experiment, she leads several very important studies through the momentum correlation method, which is so-called the femtoscopy study. This work accurately measured the interaction between various particle pairs such as di lambda, p cascade, p omega, etc. And the results are published in high-impact journal like Nature and Physics Review Letter. And I believe this is also our topic today. So let's welcome Laura, please.
So good afternoon to everybody. It's a pleasure to be here with you today and to talk to you about the beautiful story we could put together in the last year within the Alice collaboration at LHC to deploy a new method to study strong interactions among hadrons and also to investigate which is the impact for the physics of neutron stars. So I'm Laura Fabbietti. I'm currently a scientific associate at CERN for still 1 month. And after that, I will return to my beloved TUM University. So let's start with main interest that we have in nuclear physics, or at least my group has within nuclear physics. This is the study of a residual strong interaction among hadrons. If you look at the running coupling constant of a strong interaction, alpha S as a function of the exchange momentum between two, let's say, degree of freedom, you have this running coupling constant that which values characterize the confinement for small q value and large distances, and asymptotic freedom for large q values and small distances. Within asymptotic freedom, we have basically the behavior of quarks, gluons interaction, which are described very well by perturbative QCD. Although if you go in this regime, which is the regime that characterizes the residual strong interaction among hadrons, where distances are of the order of a Fermi and exchange momenta of the order of 1 GeV, perturbative QCD does not work anymore because the coupling constant is too large, basically. And this is where strong interaction is not yet described very precisely. Normally, if you think about the interaction between a proton and a neutron, you can imagine that this interaction can be modeled, assuming that you exchange a pion. This is, let's say, the basis of effective theories which consider hadrons as a degree of freedom and are normally constrained to experimental data to extract models that describe the interaction in a precisely manner. And which are these experimental data? So for nucleon-nucleon interaction, we have a plethora of scattering experiment. And here you see only one example of scattering experiment where the shifts as a function of the energy can be deduced and partial wave analysis can be carried out. And in this realm, the data are very good, and so meaning that the precision of the data then allow to constrain this effective model in a precise manner. But when you introduce strangeness in the system, you try to scatter now a lambda hyperon on a proton, you can see immediately by the naked eye, comparing these two plots, that the statistical error blows up. It goes for a few percent to 20, 30%. So clearly, when you introduce strangeness, 1 unit of strangeness in the system already are constrained to theoretical models, it's much more difficult. And if you increase this with strangeness, so if you, for example, look at psi, hypernuclei or psi scattering, we don't have data for psi scattering on nucleon. And you have just like single events. Here you see the trace on emulsion that the decay of psi candidate hypernuclear leaves, which is basically is only a single event, right? We have additional information about the where hyperons are involved by looking at the property of hypernuclei, like for example, the hypertriton lifetime. But it's clear that the more strangeness you introduce, so this is illustrated here in this line, when from left to right, you have more and more unit of strangeness, the experimental data becomes more, less, let's say, present, right? And for large strangeness content, there were basically no data before we deployed our which I'm gonna explain in a moment. On the other hand, these effective theories, they are, let's say, limited because they do not really consider quark and gluons as degree of freedom. So they are not really first principle theories. And to this end, the only way to try to look at this interaction now, not simplifying the interaction with a pion exchange, but really looking, starting from quark and gluons as the degree of freedom, the only way we have today is to use lattice calculations. And these lattice calculations are computed on supercomputers. So basically, the idea that you have a lattice with a space, and then on this lattice you can put the conjunctions, the quarks, and the lines are the gluons. And the smaller is the spacing, the more sophisticated or more precise are the calculation. Today, for example, for the AlQCD collaboration added by Tetsuo Tsuda in Japan, the lattice spacing that they use is of 0.085 Fermi. The total length of the cube, so on which the calculations is performed, is 8 Fermi. And you can see that this collaboration achieved to let's say, have pion and kaon masses which are rather close to the on-shell mass, not yet there. Anyway, this is only an example, right? Because there are many collaborations at work. But today, I'm going to show only the results by AlQCD collaboration, because this is the collaboration with whom we work together within the ALICE experiments. What is the results from this calculation? This is the local potential for any pair of choice for which you want to investigate the interactions. Here you see the example of the local potential obtained for nucleon psi interaction, so as a function of the interparticle distance. And you can see that there are 4 curves because each spin and isospin combination will lead to a different interaction. So, and this is basically what can be produced by the lattice calculation. Meanwhile, on this Fugaku supercomputer, which is a 500 petaflop machine, and I think to this end, the most powerful machine in the world. And now, clearly, I want to convince you today that we have an experimental facility that allows us to test this potential for the first time. And this is actually very interesting because basically the calculations are more stable if quark mass is heavier. So the precision is improved. So here you have a kind of situation in which For lattice calculation, you have good data, let's say, for large strange content, but you don't have experimental data. And this is exactly where we come in, and we came actually in, and we kind of revolutionize the picture, because we were able for the first time to provide data to test this first principle calculation. Okay, but now I want to tell you what I have in menu today. So everything is done with Alice detector at the LHC. And the technique which allow us to study interaction is called endoscopy in small systems. So first I will try to explain to you how this technique works. And then I will show you basically 3 sets of results. The first results interest the results for hyperon-nucleon interactions, and how, by looking at study this interaction, we were able to test chiral effective theory and first principle calculations based on lattice. Then I will try to explain how these findings have impacts on the neutron stars properties. And then I will show you how we want now to move forward and go from 2 particle interaction to the analysis of 3 body interactions, which is basically the future for us. Okay, we start with explanation of the technique. So we start with a collision. We are at collider at LHC, so the machine with the largest possible center of mass energy in the world. And after the collisions, you will have, let's say, a system. In PP collision, it's not really a fireball, but it's you can imagine this as an hypersurface from which particles are emitted. This is very important because it's an ingredient that plays an important role in the femtoscopy technique. And then basically many particles are produced. In the analysis of PP collisions, we focused on events where at least 20-30 particles are co-produced per each collision. But then we focus only in each event on the pair of interest. So we just really look at the 2 particles among which we want to calculate the interaction. And for these 2 particles, which are produced as a certain distance r, which in principle we do not know because we cannot measure this, we measure although the 2 momenta, the 3 particle momenta, and we can evaluate in the so-called paired reference frame, so in the reference frames in which the 2 particles are emitted back to back, the relative momentum K star. And we can build then experimental correlation function, which is basically built taking pairs with a given K star producing same event, and normalizing these distributions to the same, let's say, histogram obtained by combining particles which come from different events. If you consider this function key, K star, this is just like a correction for possible losses of efficiencies. But basically, this simple experimental observable has been demonstrated in the 70s already to be equal to the integral of the hypersurface distribution, so the so-called emission source, with the distributions of the distances between the 2 particles, multiplied by the relative wave functions between the 2 particles, which is a function of the relative momentum and relative distance, taken to the square, and then integrated over all space coordinate. So you can see then, if you believe now this equation, clearly by measuring a correlation function as a function of K star, you have access to the 2 particle wave function where the interactions is hidden, right? Because if you have the interaction potential for 2 particles, you can solve the Schrödinger equation and obtain the relative wave function. And hence, given a potential, you will have a wave function. So you can study this wave function provided that you know, right, the source. So the first step that I have to, let's say, make is to convince you that we have a solid data-driven model that allow us to determine this emission source. But basically, once we have the source, given a potential, the Schrödinger equation gives us basically the relative wave function. And so then the correlation function allows us to test different potentials. I just want to make an example how this correlations looks like. Let's assume now a source parameterized with a Gaussian distribution. This is normally what we use, and characterized by a parameter R0, which will be basically the width of the Gaussian, okay? And let's take the example of these two interacting potential. The red one is a mere repulsive potential. The green one, it has an attractive part and then a repulsive core. So given these two local potential, one can solve a Schrödinger equation for two particles and obtain the relative wave function. So now I have the source, I have a wave function, and I can use the CATS framework correlation analysis tool using the Schrödinger equation that I developed together with my students a couple of years ago at the TUM to basically obtain the wave function. And then basically with the help of this equation, we take the source, we multiply by the wave function, we integrate over the space coordinate, and we obtain here the correlation function. Which features does this correlation function possess? In case of a repulsive potential, the correlation is between 0 and 1. In case of an attractive potential, the correlation is larger than 1. You can see here that the green curve goes a little bit below 1 because you have a repulsive core, right? And you can also see that for K star larger than 150 MeV over C, or 200 MeV over C, the correlation is equal 1, meaning that you do not see the effect of the interaction anymore. So it is clear that these kind of measurements, if you want to study now the potential and the interaction, you need to have an experiment which allows you to measure a correlation function down basically to 5 MeV over C. So you need really to be able to resolve very small relative momenta, because above 150 MeV over C, you don't see anything anymore. So there is also another way to, let's say, perform the correlation function, starting not from the potential, but from the scattering parameters. Indeed, given for a given spin state, the effective range and the scattering length, one can use the Leibniz-Ljuboschit formalism, where the correlation function now has a bit it's not an integral, let's say, but as this phase as an analytic form, where the component, which are here indicated in pink in the formula, represent the scattering parameters, and the component in green are basically referred to the source. In order to obtain this analytical formula, which is based on effective range expansion, and that works well for rather large source, we will see in a moment what large source or small source means. You assume to have a Gaussian source function, and then you come to this analytic formula. And basically, the only parameter you have in the formula related to the source is the sigma of the Gaussians, which is this R0 parameter. Okay, I want to show you the two ways to use the correlation function, because in our study we employed both, depending on which channel. This is something which was done, put forward by Leibniz and Ljuboschit already in the 80s. Okay, let's look at the data, because the ALICE machine at the LHC is key to do these kind of studies. So the ADIS detector is actually a multi-purpose machine. The data set that here I'm concentrating are not the ion collisions, as often is described by ALICE, but we consider here only the proton-proton 13 TV data set with the so-called Ig multiplicity trigger, and we have about 1 billion events at our disposals. And why can we do these things with ALICE? First of all, because with ALICE you produce plenty of hyperons, so you can study really the interaction among hyperons and nucleons, even among hyperons themselves. But this is true for all the LHC experiment. But the advantage of ALICE is that it is extremely good in PID. And not only the PID of protons, kaons, pions, and deuterons, but it can also reconstruct weak decays. It can reconstruct, for example, the weak decays of lambda, psi, omega, you can even reconstruct the electromagnetic decay of sigma or the strong decay of phi. And in order to, let's say, demonstrate that all this is true, I have here some performance plots. On the left-hand side, you see the energy loss in the TPC as a function of the momentum for the proton-proton collision at 13 TeV, where you can see basically with the bare eye that already the energy loss measurements allows you to distinguish between kaon, proton, deuteron, and tritrons. And then here on the right-hand panels, you see the invariant mass reconstructed for lambda, psi, omega, and sigma 0, starting from the daughter particle. And you can see that even in the case of sigma 0, where the daughter particle are a lambda hyperon and a photon, right? Although the signal to background is not so good as in the other cases, a clear peak can be let's say pinned down, meaning that for all these hyperon, we can really reconstruct them, assign the mass and assign the momentum. And then we take protons or deuterons, and then we can make pairs and study the interaction, okay? Okay, so one thing which, before I go to the interaction, I have to convince you is that we have a reasonable knowledge of the source. Yes, so when you collide small systems, so proton-protons collision, for example, you have to consider that even in proton-proton collision, you can have anisotropic and radial pressure gradients. And this leads to a different effect on different masses. That's why the source, it's not a simple Gaussian with one radius for all pairs, but it has been seen in data that the source has different, so is a function of the distance r and the parameter r core, let's call, that is not a constant, but is a function of mt, of the transverse mass of the pair. Okay, so we have a so-called MT scaling, which is observed also in heavy ion collision. You can see it also in PP. So you need to measure basically the source for different MT. But then there is another point, because when you have like small colliding system, the source that you will obtain is as a sigma of 1 Fermi, yeah. Which is good if you want to study the strong interaction, because this is exactly the range where the strong interaction is visible. But on the other hand, whenever you look at a final state particle, so like, for example, imagine we want to look at the proton lambda pair, you have to consider that there are many resonances, strong resonances like delta plus plus and star, sigma stars, that can decay after a distance c times tau of about 1 Fermi, between 1 and 2 Fermi, in this final state. So meaning if you have already a small distance and then you want to be accurate in determining this distance distribution, you have to consider the contribution of these resonances, okay? Because many, for example, of the proton and the lambda comes from this resonance. The primordial fraction for protons is estimated to be 30% at typical LHC energy, and for lambda is also 30%. How do we know that? We know it because we have statistical hadronization models that are rather successful in describing the fields of these resonances. So this means that the Gaussian model alone is not sufficient. You have to append to a Gaussian an exponential tail, and this exponential tail will have a parameter s, and s depends on the final state because it will include the specific resonances which are associated with the final state. Okay, putting this thing together, so we could develop a data-driven source method, which is a universal source, meaning that you have only one radii as a function of mt for all the particle. And this is basically would give you now the hypersurface where either primary particle or resonances are produced. Then you have to append the resonance, and this generates, this together with the fact that different pairs have different MT distribution, leads to the fact that the probability density function of the distance, meaning the source multiplied by the phase space factor 4 pi r squared, I mean, it's different if you have a proton-proton pair or you have a proton-omega pair. For proton-proton, you see the maximum, the most probable value of a distance is around 2 Fermi. For proton-omega is around 1.2 Fermi. But what can you see in this probability density function? That no matter which pairs you take, you have a good percentage of pairs which distance is lower than 2 Fermi. And this is one of the key aspects of the reason, of this analysis, that looking at PP collisions allows you to have a certain fraction of your pairs, which are really located at small distances. And this is the reason why you can investigate the strong interaction. If you look now at the so-called effective radius for each pairs, which is obtained by taking the core radius and appending these resonances, you can see that for all the pair of interest, the effective radius is of the order of 1 Fermi, okay? Well, meaning that then the most probable value of the distance is between 1.5 and 2 Fermi. Because this R is not to be confused with the average distance. This is really the sigma of the Gaussian. Okay, so this plot should convince you that we have the source under control. So we really know how big the source is. So now we can proceed and study the interaction. And here I want to show you basically all the interaction we have studied so far. So which, as you can see, it's a huge work that has been done. So I have organized them in these two, let's say, axes: strangeness content and baryon content. And each interaction that has been studied is a puzzle piece. And the red puzzles were those that before us were never investigated, while green pieces correspond to interaction which were already known and we can use as a benchmark basically for the method. And the, let's say, the check list, the green check list, are those interactions for which we have results and we have also a publication. But actually, clearly, I cannot show you all these results. Today, I want to focus on the results, which I circled in blue, which are the lambda n, sigma n, psi n, and then three-body NNN and lambda NNN interactions. And why do I want to focus on these interactions? Because these are the interactions which are more important for the physics of neutron stars, as you will see in a moment. Okay, let's start with the strangest equal one case. So the case of the lambda-proton interaction. So before we came with the measurements, we had, let's say, the scattering cross-section of lambda proton going to lambda proton obtained in experiment, in bubble chamber experiment at CERN in the 80s, where the cross-section here can be compared to leading order and next to leading order calculations. And you can see that basically both calculations are, let's say, similarly good to describe the data, also because the experimental data have sizable errors. And that this peak here that you see around 600 MeV/s, which represent the so-called cusp, so the channel in which the sigma n channel couples directly to the lambda n channel at the threshold. It's only predicted by the theory, but experiments basically cannot resolve this structure. And most recently, the class collaboration repeated this kind of experiment at large energies, for large momenta. So basically, if you want here, you finish at 900, here they start around 900. And they measured this cross-section, improving the statistic at large momenta. But the region of large momenta was still, let's say, since the 80s, completely untouched. But then we came and we put last year a paper on the archive that is going to be published soon. And here you can see our measurements. Here, the K star in comparison with P lab is basically nothing than P lab divided 2. So, and you can see two things. First of all, that for small K star, you have now a statistical precision, which is 30 times better than the scattering data. You can see that now this cusp structure can be seen experimentally, and that even the best of a calculation, which is an X leading order calculation carried out in 2019, produce as, let's say, as a rather reasonable agreement with the data, but still there is a tension because there is an n sigma of 3.9 integrated between 0 and 300 MeV over C. So what does it mean? That these data now they challenge the calculations, right? And this data shows for the first time the evidence of a cusp in the two-body scattering. If we go to another channel with strangeness equal 1, we have here the proton sigma 0 correlation function. And okay, I forgot to say here, sorry, one important thing. The correlation function that you see here is larger than 1, okay, for lower, for values of K star lower than 120, because the proton lambda interaction is mostly attractive. Although you can see that the interaction goes below 1, right, close to the cusp, probably because we are a bit sensitive to a repulsive core. Yeah. If we go to the proton sigma 0 interaction, where the sigma 0 is reconstructed out of electromagnetic decay lambda gamma, you can immediately see that things become more difficult. We can measure the correlation function, but the experimental uncertainty is huge. The statistical uncertainty is huge. And now, in order to see whether we have interaction or not, you should not compare this interaction to the unity, but to this gray line, which is the baseline. And why so? Because there is background. And in correlation function, when you have a background, you can basically compute the correlation that you would see if you would have only background. And this is this gray correlation function. So meaning that the difference between the data and the gray correlation function tells you that the interaction is probably slightly attractive because the data are above gray band, but with a very few significance. So what does it mean? In few words, that for proton sigma 0 interaction, that we compared also to several calculations, we cannot yet resolve the calculation and decide which calculation is best. But we can see that the interaction is shallow. So it's slightly attractive probably, but it's not really an evident interaction. Okay, keep this in mind because we will use this for the equation of status Newton star in a moment. Then we want to go to the sector with two strangeness units, so proton psi minus, and there. So I told you that more strangeness you have, more precisely are the data of lattice QCD, and that's why we can take now these potentials that I showed you at the beginning. Now we know what to do with this potential. From the potential, we solve the Schrödinger equation, we have a wave function, then we plug in the radius for the proton psi minus source. And here we have two values, 1.4 Fermi and 0.95 Fermi. Why two values? Because we have analyzed this interaction in two colliding systems, which are proton-lead collisions, where radii are slightly larger, and proton-proton collisions, where radii are slightly smaller. And you see in these two cases, the publications, the published results, where you see the correlation functions, which are in both cases larger than 1. Okay, so meaning attraction. But okay, proton psi minus, they are positively, and I mean, they are opposite charged, right? Meaning that you have anyway the Coulomb attraction. And the question is, do I see here only Coulomb or do I see also the strong interaction? And if you look at the green curve in both diagrams, so this represents the prediction calculated with cats, assuming that you have only Coulomb interaction. And what do you see here? That the data are above this green curve with a large significance, meaning that there is an additional interactions that attract proton Xi minus. Now, if you solve a Schrödinger equation considering the Coulomb interaction and the lattice attraction, you obtain the orange curve and the pink curve in the two cases, which matches the data perfectly. So what does it mean? Basically, the data that we have measured confirmed for the first time the existence of an attractive strong interaction in the proton Xi minus channel, and also confirmed that the lattice calculations are all right, that they are reproducing our data very well. So you can imagine this was a very good success, not only experimentally, but also for the lattice people, because we could, as first, test their calculation. Okay, now clearly you want to know what has this to do with the physics of neutron star. But so far, I just described the interaction among hadrons and showed you that we have a way of describing them. But what has this to do with the physics of neutron stars? Okay, neutron stars are interesting objects because they have a very small radius between 10 and 15 kilometers and a very large mass. So consider between 1.1 and 2 solar masses. And this leads to the fact that basically the interior of neutron stars is not dense as, let's say, the atomic world, which characterizes the Earth, but it's as dense as nuclear matter, probably even denser than nuclear matter. And so these are amazing objects, because the question is, okay, on their crust we have neutrons, electrons, but what is inside? I mean, how does really matter under string condition behaves? Do I have only neutrons packed together, for example, like you see in this cartoon, or can I also produce a new degree of freedom? And why can you produce new degree of freedom? Mainly because theoretical calculation tell us that if you increase the baryonic density, as it is shown on the x-axis of this left plot, the baryon fraction in a system transforms so itself from containing only neutrons at the beginning, and then proton and electron because of beta decay, into naturally converting nucleons into hyperons. So at certain densities, which are not so large, so already at 2 rho 0, you should have lambdas popping up or xi popping up. And now this, let's say, appearance of hyperons within neutron stars is driven by the interaction. So you can see here, for this particular calculation, you assume to have 3 values of the so-called single particle potential. So for lambda, sigma, and psi. What is the single particle potential? This is the average action that nucleons have on the hyperon. So this is a little bit like a Wood-Saxon potential in nuclear physics, but now it involves the hyperons. And these values here tells you that for lambda, the single particle potential is attractive, minus 30 MeV. For sigma, it is repulsive, plus 30 MeV. And from psi, the single particle potential is slightly attractive, minus 18 MeV. And these are, if you want, numbers which are partially constrained by experimental data. Actually, when this calculation was done in 2010, only the single particle potential of lambda was constrained to hypernuclei. The other 2 values are, if you want, like fantasy value. And what happened if you change this value? Yeah, you see from here now, I go from these lights to these lights, and the single particle potential lambda stays the same, minus 30 MeV, but I change U sigma from plus 30 to minus 30, and I change U psi from minus 18 to minus 28, and immediately the lines, the appearance of the lines completely is modified. First of all, I mean, in this case, you have only xi's and lambdas, while in this case, you obtain also sigmas, and also the position in density where these hyperons appears is changing. What does it mean? That you need to know the interaction and the single particle potential in order to know which kind of constituents you will have in your dense matter. Okay, because obviously if you have an attractive interaction, it's easier to produce particle, while a repulsive interaction will push the threshold in density for the production of this particle at larger values. Okay, so now let's see what we can do now, what we learned with femtoscopy. I showed you the correlation function, and the correlation function just tells us how the two-body interaction works. Yes, but the next leading order calculation is able to extrapolate the single particle potential. And now what you see in this middle panel is the single particle potential as a function of the density for two calculations. So the magenta one corresponds to next leading order 19 that we kind of confirmed or prefer. And you can see that this potential stays attractive all the time, and even for large density. While the previous version of the next leading order calculation, which our data show tensions with, I don't show you the figure, but you have to believe me, have a different single particle potential. The single particle potential shows a repulsive core for large density. So meaning that now the equation of state is slightly softer, okay, because you have only attraction for the lambda. Okay, so this is the way we infer on a single particle potential. We don't really do it ourselves, but the theory people do it. We provide the anchoring of a theory for two particles interaction, and then the theory produces the single particle potential. The same can be done for the sector with two strangeness degree of freedom. So we have seen we have a two-body interaction for the lattice confirmed. Now we can go and ask the theoretician what is the single particle potential for Xi. And this plot shows you the single particle potential in a symmetric nuclear matter, meaning same amount of neutrons and protons, and the lattice calculation predicts a slightly attractive potential that then turns into repulsive. Although when these calculations are carried out in pure neutron matter, the single particle potential it's slightly repulsive and has a value of +6 MeV. So now, if we now combine this information, okay, of single particle potential into, let's say, the prediction of the density variation of the baryon content, we can see that a new picture appears. So now you can see that these single particle potential have been now updated to the values, to the constraint of the Alice data. We have still a very attractive interaction for lambda, but slightly less, -20 MeV, 28 MeV. We have a slightly repulsive sigma interaction in pure neutron matter based anchored to our data, and a slightly attractive interaction for Xi in symmetric nuclear matter. And this now shows basically that lambda and sigmas appear rather early, but Xi appears rather late. Now, this diagram, okay, is nothing else than an equation of state, because basically this diagram tells you at which density which particle will be there. And since you know the interaction, you also know the equation of state, which is nothing else than the pressure against the density for the system. And so if you have the equation of state, these, let's say, lines can be translated one-to-one to a line on the mass versus radius for the neutron stars. Okay, so I mean, I know this passage is a little bit abrupt, but you have to believe me. This plot on the left-hand side is one equation of state, and the equation of state can be translated one-to-one in a mass versus radius. And this line here crosses the measurement or heavy neutron stars. So it seems to be in agreement with the measurement of very massive neutron stars. So now, this is for sure not the end of the story. This only shows us, if you want, the roadmap. How can you constrain two particle interaction, extract single particle potential, and then extract an observable physical neutron stars? As you can see here, this line does not yet have an uncertainty. And we need to propagate the uncertainties of the experiment, of the theoretical model, in order to really know which kind of line we have. But we can do this in the next year. And actually, the key now for the future is to move on and think about three-body interaction. Indeed, three-body interactions are still important in the physics of neutron stars, because it's true that the strong force is a force of first neighbors, but three-body and probably four-body interactions are very important also in the physics of nuclei. So in the physics of neutron stars, we play a role. So that's why we have started doing this very crazy project of looking at three-particle correlation. So here, basically, instead of doing the correlation with two particles, you do it with three. Instead of talking about K star, you talk about a Q3 momentum, which is defined here as the sum of the three invariant momentum taking permutation of pairs within the triplet. And without further ado, I show you the measurements done again in PP collision at 13 TeV for triplets of protons, so p+Pb correlations and p+ lambda correlation. And now you can see that as a function of Q3, you have for p+Pb, you have a kind of complicated shape, right? I mean, as usual, the correlation goes to 1 for large values of Q3, and then here it goes up and it goes down and it goes up again. Okay. While for proton-proton lambda, I mean, you seems to see that it goes up, but errors are huge. Now, how can we interpret now this three-body correlation function? So we want to look at the three-body interactions, but clearly it's not that the three-body correlation function tell us only about the three-body interaction. Indeed, I mean, the cumulants paradigm tells us that when you measure triplets, okay, you can extract the genuine three-body correlation, which comes from three-body interaction, only if you subtract correctly lower order correlation. Because clearly, if you have a triplet, you have like two-body interactions with the third particle as spectators. And you have to kind of subtract that if you want to access the genuine three-body interaction. Okay, this can be done. There is a way of doing this. And actually, we have developed two ways of doing this. So one which is measured is based on a data-driven method, and another one which is based on the so-called projector method. I will not go into the detail of that. The paper is going to appear in the archive in 1 week. What it's only important is that this method allows us to subtract basically from the three-body correlation, the cumulants. And this is now the results for triplets of protons. So what can you see? This cumulants is 0 above 220 MeV/c, meaning that there you don't have any signal of genuine three-body interaction, but below 250, you have a negative cumulants, which have a significance of 6.7 sigma. And so we see an effect due to probably three-body effects, so three-body interaction. We don't know exactly yet what this effect is due to, whether it is Pauli blocking at three-particle level, residual long-range Coulomb interaction, or maybe really three-body strong interaction. We need a calculation, which is currently being developed by some colleagues at the Pisa University. But for sure, now experimentally, we see a signature. And now for three protons. Now, for the physics of neutron stars, we need the hyperon. So that's why we look at proton-proton lambda. There, if you look at the cumulants here, the significance with respect to the zero, right, line, it's only 0.8. So one cannot draw any conclusion, right? But the good thing is that run 3 is starting now in 1 month, and in 2 years we will have factor 500 more in statistics. So I am rather confident that we will be able to pin down the three-body interaction with a completely new method. Okay, I have come to my summary. I hope I could convince you that femtoscopy in small system is really a smart tool to study interaction, that we have the source under control by means of our universal source model. I showed you some of our results in the interaction, focusing on the hyperon-nucleon interaction. And I hope I could show you at least the path that leads from the two-body interaction through the single particle potential to the property of neutron stars. And finally, we really hope that with the high statistic measurement, we will be the first in the world to pin down precisely three-body interactions for hyperon and nucleon. And who knows, maybe much more. Thank you very much for your interest and for your attention.
Okay, thanks, Laura. Thank you very much. So first, for this very beautiful talk, I believe it's a very good overview talk about the femtoscopy study and highlighting the recent studies in this direction. I believe it's very thought-provoking, and it should be very helpful to not only the expert doing the Heavy-on, but also for because we have many audience are amateur in this region. So now, as always, this is the question time. So please feel free to raise your hand or type your question. We're gonna handle one by one. Okay. Okay, we have the first question. Jinghui, please.
Thank you, so Lola, for a very nice talk. I have two questions. One actually is on the proton cascade. No, the cascade sigma interaction. Can you? And the other one is the interpretation to the equation state of neutron star. Can we go to slide 32?
This one.
Yeah, this one. Yeah, this one.
Yeah.
Proton sigma 0. So the actually, yeah, I should read your paper more carefully, but please allow me to ask here. So have you checked? So the actually the gray area here is for the background, right?
Yes, exactly. This is basically combinatorial background of below the photons. If you, I mean, is so the sigma 0. It's obtained from the invariant mass lambda gamma, right?
Yeah.
And you have a monochromatic gamma, which we cut, so it's 80 MeV. But obviously you have many combination of the plus and minus, because the gamma is determined by a conversion. Okay, so we look at a plus minus conversion signal inside, and obviously you have a lot of background. And the reason why this correlation function is not flat, it is because you have combinatorics of E plus E minus, but you still have a lambda. So when you combine it with a proton, you have a residual lambda proton interactions, which gives you a signal. And this is why basically this gray band has, let's say, a strength which is not flat, you know, because you have a residual lambda proton interaction, which is back.
So that's possibly is also a little bit attractive if you are saying that the proton are gamma. Or not?
Yes, this is attractive. The background, let's say, the background is attractive. Yes, it has an attractive effect. So it looks like an attractive interaction, right?
Okay.
But it has nothing to do with the genuine sigma 0 proton interaction. That's why basically, if you want to, you know, consider I mean, this difference here, you see?
There is sizable difference. So my question is, another question, have you also compared the proton lambda here to see if there's a difference between the proton lambda and the proton sigma 0?
Yes, so we compared, and there is a huge difference, because if you go,
I think the previous,
I don't have a plot,
but
if you go, so if you go here, you see, the correlation function of proton lambda goes up until 2. Right?
Okay,
And
okay,
if you look here, this is 0.2, so it's really factor 10 stronger.
Okay.
Within errors, right? We have to improve the precision and even measure the charge sigma with the protons, but it's a factor 10 larger.
Okay, a small question related to this. If you go to your universal source, actually the proton cascade, the proton sigma actually is if you go to empty plot, can you go to the empty plot? I think this page 26.
This one?
Yeah, this one.
Yeah.
So yeah, the protons sigma 0 is if you look at the empty, the proton sigma 0 actually is larger than the proton cascade minus. So can you expand a little bit why it is here?
Yes, that's a very good question. Thank you very much for asking. This is due to the reconstruction of techniques, because basically the sigma 0 is reconstructed from lambda gamma, right? And the reconstruction for the photons works only for the larger PT, because basically you need to have some PT to have the A plus minus with sufficient PT to be reconstructed, because if A plus minus are too soft, they do curls in the TPC, and you cannot. So basically, because you have to think this correlation analysis is not efficiency corrected. We just take what we measure, right? This is also why it's so, and that's this is really the analysis. It's not, let's say, it's not nature. It's only those which we can reconstruct are located at this larger MT.
I see. So please allow me to ask another question on your interpretation to the equation of state of neutron star. Can you go to slide 42?
Absolutely, I'm going there.
I think that
Yes.
Okay. So if you look at the single, I think that the single lambda potential. Yeah. I haven't go there yet. So
do you see IMS 42? You don't see?
Yeah, I have not seen, but okay, but I already picked. Yeah, here it is. Here,
I share again. Maybe it's a bit in delay. Oh, do you see?
Yeah, I have seen it. Okay, thank you. So the question is that if you go to a very high density, actually the lambda, if you go to very high density, actually the reduced lambda access to two solar mass region with a very high particle number per baryon, which is very high rate. This is this is kind of how to say, I think that it's very difficult to understand. My question is that, so how you obtain this single lambda potential? Do you have a result from the lattice QCD calculation?
Okay, no, I mean, this is because, I was a bit fast on that. So this calculation has been done together with Jürgen Billich and published in this review paper, which I wrote together with two colleagues. But basically, it's like the following. This, so wait, I have, okay, so this value is a bit of a patch. Okay, this, okay, I not annotate. Okay, yet no. Okay, so this is the usual single particle potential for hypernuclei. It's not changed. It is always either minus 30 or minus 28 MeV. So they did not, Jürgen did not do much. Then what he modified a value for the single particle potential of sigma. For some reason, I don't access anymore my mouse. But anyway, the single particle potential of sigma and psi, okay, it was modifying them. Sigma, he took our correlations, the single, and he took one curve that goes to our correlation and evaluated the single particle potential from the theory. And from the psi, he took the results from the lattice calculation that I showed before in the previous. I don't know. I cannot. I have no problem. Can somebody?
I can hear you. I can hear you. We can hear you.
No, but I cannot move. I don't know what happened. I cannot move. Okay. Okay, now I will, my computer is a little bit, I don't know what happened. Okay, now, so basically it takes this one, okay, for the single particle potential of Xi minus, it takes the lattice calculations.
Oh,
which
this
are
is for
conformal
lattice.
data.
Yeah, yeah, okay.
This is for
okay.
lattice, yeah, because the single particle, so I try to explain it here. We confirm the two-body interaction, then we take the single particle potential from lattice. So basically, it did a kind of mixture. The Xi here is from lattice, while lambda and sigma, they are from chiral effective field theory.
Okay, okay, okay. Thank you, Laura.
Hi, Laura, are you still connecting? It's okay.
Yeah, I'm here.
Okay, good. Okay, so thanks for the and next question, Guoliang.
Hi, Laura. Very nice talk and beautiful measurement.
Thank you. I don't hear. It's me. We was.
Oh, he's mute.
No, Guoliang,
he's
somehow
he's
you.
Okay, he's muted.
I lost my connection. Okay.
Okay, I think the connection is not that good. Maybe I also, or mine, or I don't know.
No, you are fine.
Can you hear me?
Yes.
May I ask?
Yes.
Maybe my question is too naive to Professor Laura. You show me lots of measurement from the PP clearance. Why I don't measure the correlation in light clearance?
Because I will show you. This is, the smart idea I had that nobody believed into 6 years ago. Everybody told me that this will not work, but they were not right. The main reason why PP collisions are better is this plot, because this is the source radius, okay, so the sigma of it, which is, as you can see, is takes value from as a function of MT from 1.1 down to 0.9. Okay, so 1 Fermi. Now, if you go and you do the same in heavy ion collision, you can do the same, but then the radius will be 6 Fermi, 5 to 10 Fermi. What does it mean? That when you look at then this density function, okay, the peak will not be at 1.5 Fermi, but it will be at 8, 9 Fermi, okay? And then if you now, let's have a look at a typical strong potential, so that, for example, let's look at this potential, right? Okay, this potential is non-zero only up to 2.5 Fermi. If you now go to 8 Fermi, this potential is 0. So meaning that if a distance at which particles are produced, like in heavy ion collision, is too large, your correlation function will be flat. You don't see anything. Yeah. So the good idea.
I think you always can find pairs. They are very close, even in the heavy ion clearance, right?
No, I didn't understand. Can you repeat?
I mean, we always can find pair like proton Casei pair, which are very close, even in the heavy ion collision.
No, not so many pairs. No, it's not so easy. You have to select very, very large MTs, and then finally the statistic is poor and distances are still 3, 4 Fermi. It's not, doesn't work. I mean, if it would work, if it would work, these results would have been obtained in heavy ion collision, but people were not able to do that. They didn't get a statistic. So in principle, you can select very focused pair, but you do not. And also, there is also another reason. I mean, in an heavy ion collision, you have QGP formation, right?
Yes.
So, and hadronizations and things like that. So it means that basically this model that we have here, so where basically we have only empty scaling plus resonances. In heavy ion collision, a source mode much more complicated, because you need to know really when particle hadronize. I know that some people think that particles hadronize all at the same time, but maybe it's not true, right? Maybe strangeness hadronize before or later probably than non-strange light hadron. So this is not so easy. So to define the source model for heavy ion collisions. So it's not impossible. I don't want to say it's impossible, but I think it's easier to do it in PPE. So if you have the rates in PPE.
But yeah, on the other hand, I think it's useful to measure the correlation in hyperon-nucleons, because for neutron star, for your second topic, so we know the neutron star is always high density, so with high mu b. So actually, I think the PP measurement, the data is for the small mu b, the correlation. I mean the interaction potential you measured from the PP is more suitable for the less mu b case, I think. For the high,
yes, you are right. Okay, then you are right completely. If you have, if you look only at two particles, so I want to show you a sketch to tell you, anticipate a little bit. Okay, if you look only at two particles, you are completely right that this is basically vacuum, right? More or less.
yes.
So
yes.
it's not large mu b. Okay, so that's true. So then it would means like that you want to determine the interaction in an environment with large mu b, like for example CBM. This will not be heavy ion at the LHC, because at the LHC the mu b is 0, it's very small, right? So you would need something like yeah. Okay, only now this kind of measurement within CBM, so they can be probably done, but this requires another scheme, because I mean, just measuring correlations in heavy ion collision in CBN will not give you the interaction at large mu b. It's not so direct, yeah. So, but it's doable. Maybe I don't know, either myself or somebody else will work on that. This is a possibility. But then I want to put your attention on the following things. Look at now at these 3 particles right here. So you put 3 particles, maybe you put even 4 particles at very small distance. Okay, so when you put 4 particles at very small distances, as you can do at the LHC if you have enough rate, you mimic density. So my vision is that we will be able to emulate large mu b at the LHC, looking at many particle correlations collimated in space. And in 2 years, you will invite me again to see how I have demonstrated that. So
yes, but it's also more difficult to measure the 4 particle correlation. Yeah, even
that's
for 3
right,
particle.
but this is more difficult, but it's not impossible. And if it would not be difficult, it would also make no fun, right? So
okay. Yes, I agree. Yes, thanks for your explanation. Thank you.
Thank you very much for your question.
Yes, thanks, Guoliang. And yeah, since we mentioned this, just a very quick question from my side about the multi-particle correlation in the momentum space. Because in the azimuthal space, people already did a lot about the flow study, right? The 4 particles, 3, 4, 5, yeah, can be as many as possible. So for the momentum, for the correlation in the momentum space, how many have we established about this kind of framework?
Nothing. We are the first one. We are the first one doing that.
Okay.
So this is the. But that's why, I mean, we always do pioneer work, right? So because otherwise, if somebody else would have done already, me, I would not be interested. Me, I only do things which nobody else did before. So, and now going back, as you rightly observed, actually, this cumulant technique that I was mentioning right here, Kubo. So
yes, this is a general. Yeah, it can be extended in many directions.
Exactly, and this, as you said, was used in flow, right? This was what Ante Bilancic published in 2011. where he showed that Kubo mechanism, formalism can be applied to flow. And from that, we developed really like all the symmetric cumulants and cumulants. In momentum, nobody ever did that. I mean, there was one work done by Devan within the Alice collaboration, where he looked at 3 pion correlations, but in heavy ion collision to establish coherence, right? But nobody ever looked at 3 particle correlation, 4 particle correlation in small colliding system. Yeah, this was never done. So we are the first. So there is no established framework. We have to write. And that's why I did not include silly me, the publication that we just put in the archive with my group. We wrote a paper. We published actually a paper.
So we're not very sure about the physics nature about this high order cumuli in momentum space.
Not yet. We have to investigate with theory and so on. But what we know is that if we put enough particles together, this will simulate density. This we know.
Cool. Yeah, this sounds very interesting. Okay.
Yeah,
thanks.
Very
then, okay. Let's move to Song. Song, please.
Hi, Laura. Nice to meet you again online. Yeah,
hello.
I'm Song from Fudan University. Yeah. The next talk, you introduced the detail of the fermitoscopy for the strong interaction environment. You introduced the 3-body interaction Coulomb function. So the similar question is from my side, how to extract the interaction parameters from the 3-body Coulomb function, such as in 2-body, such as in 2-body interaction.
Okay, so thank you very much for this question. So there are 2 ways. So basically, the work we did so far just show that you have kind of the smoking gun using the cumulants, that you have something which goes beyond the 2-body interaction. Okay. But clearly, this is only a smoking gun. This doesn't tell you exactly the parameter of the 3-body interaction, like you just said. But then what you need is a theory calculations, which is currently being carried out by these people in Pisa, which really gives you a 3-particle wave function and then predicts the 3-body interactions. So the 3-body correlation function, considering all the interaction, considering the 2-body, the 3-body. So we need a prediction which try to reproduce these 3-body correlation functions. Okay, so this is what we need. Another possibility. I'm sorry, I have to switch off my Skype, which is disturbing me. Another possibility is to look at a proton-deuteron system. This is what we are doing currently. And because there you have a proton-deuteron system, which is a 3-body system, right, which you can study. And there we will publish soon results which show that we are sensitive to the 3-body dynamic. These are the 2 things which we at the moment we can do. We need calculations, basically, right? We're using a 3-body interactions and the 3-body wave function in free space. And this is very difficult because you have to think that in nuclear physics, these 3-body interactions are included, but in calculation which predicts bound states. So the wave functions are only the wave function of bound system. Nobody, apart from these PISA people, so far took the challenge of calculating the 3-body scattering amplitude for, as we have in CERN experiment with 3 particles, you know. But I am sure we will convince people to calculate that. You know.
Okay, thank you. We need more theoretical calculation for the correlation functions.
Right? Exactly, absolutely. That's what we need. Yeah. Okay, and more measurement. Yeah, we will do the measurement with factor 500 better statistic, and then the ball will be in the courtyard of the theory people to move forward in this field. Yeah. On the other hand, there is no other way in the world to study proton-proton lambda. So at some point we will calculate. I am sure. Yeah.
Okay, thank you.
Thank you to you.
Okay, thanks. So we have, let's have the last question because time is almost up. Laura, can you see the typing already in the type box? If you can see, I don't bother to read again.
Okay. Okay, are there any similarities and differences between PPP and PP lambda interaction mechanism? Since in PP lambda, one of the high order terms should play an important role. Okay, so thank you. So for the interaction, so first of all, the main difference, let's start from the difference, is that in case of 3 protons, you have 3 indistinguishable particles. And this makes things more complicated because clearly when you put them together, they don't want to stay together because they are 3 fermions. So you have Pauli blocking. For proton-proton lambda, you have only Pauli blocking among 2 particles, and the third is. So in the interactions, one knows that for 3 particles, proton-proton-proton, there is a 3-body force, which is in normal nuclear matter, only 10% of the 2-body forces. For proton-proton lambda, we don't know. So so basically, we do not know we don't know at all if it is repulsive, is attractive. From our data, it looks like it is attractive. Yeah. And actually, this would have as a consequence of the neutron stars that the equation of state will be softer, because if you have a 3-body attraction, this does not stiffen an equation of state. But we have to see. I don't know if it answers your question, Denia.
Okay, so anyone else? And if no one, let's thank Laura very much again. Thank you for your nice talk.
It was great. A lot of questions. It was really nice. Thanks a lot for asking.
Thank you very much.
Thank you, Laura.